I think we should wait for 2 minutes and after that we will start. Okay, hello everyone. I'm sharing my screen first. I think you all can see my screen. So, good afternoon everyone, and today is the assignment 4 and week 4 question answer session. And obviously the course name is Nuclear and Particle Physics, and the course instructor Professor Pavlos. And just a minute. So okay. Okay, so let's start about the question and answer session. So the first question, as I thought that in the previous week someone has asked me about that assignment 2 question, first question. So I thought that it should be discussed here, but I think it's already done. But if obviously there is some problem again, so I'm just going to discuss a little more about that question. So the problematic question was that what is the expected spin value of the ground state of the nucleus calcium 2043 within the nuclear cell model. So here as we can see that okay, so the question was that calcium 2043, what will be the expected spin value for the ground state of that calcium 2043. So calcium 2043, if I write here, I'm just telling very briefly about that question because it's already done so many times before. So here I can see like that z equals to 20 and n equals to 23, which is nothing but 43 minus 20. Okay, so now just coming to the nuclear configuration of 23 number of nucleons. So here if n equals to 23, then the configuration will be 1s half 2, 1p 3 by 2 4, sorry 3 by 2, and then 1p half 2, then 1d 5 by 2 6, and 2s half 2, and the last one will be 1f 7 by 2, and it will be 3 because the total number will be 23. So like it is the ground state configuration. So if I just write the ground state configuration here, So this will be the state, valence state 1f 7 by 2, and there will be 3 particles 1, 2 and 3. So as I already told you before that it will be okay. Okay, so it will be like plus minus, I mean up and down, and one will be, let's say, up. So that means as a whole the j value will be I value will be 7 by 2, and if L equals to L equals to 3 as f state is there, so that means minus 1 to the power L, which is minus 1. So that means the spin parity of the ground state will be 7 by 2 minus. So the main problem was arises when in that question the answer was 5 by 2. Correct answer was 5 by 2. So I asked sir that it should be 7 by 2 minus. Then he said that okay, it is a typo, and we will reevaluate these things with the value of 7 by 2 minus. So obviously, as you already told that it should be 7 by 2 minus, it's absolutely correct. And so I am just giving that explanation for your reference, and we will go ahead right now for this week. Okay. So the first question of today's lecture is like kinetic energy of alpha particle in an alpha decay is 77.68 MeV. If the Q value of the decay 7.82 MeV, what will be the mass number of the parent nucleus? And it should write integer value. As I already told you before that the parent nucleus's mass number should be of the order of integer, like it should not be a decimal number. So that's why it is the question is also saying that mass number of the parent nucleus, please write the mass number of the parent nucleus in integer value. Okay, so the question is basically what? The question gives us like that type of question is let's say alpha decay it is there. It says that it is a alpha decay. So alpha decay means what? So alpha decay means as I can write here that x, z and a, it will go to let's say y, z minus 2 and a minus 4 plus what? Plus alpha 2, 4 is there. So this type of expression will be there for alpha decay, and what they are trying to understand that they are just going to say that okay, the kinetic energy of the alpha particle, that means this has a kinetic energy which is 7.68 MeV, and okay, and the Q value for the total reaction is 7.82 MeV. So then if these two condition is there, I mean if these two data is given, then what will be the value of mass number of the parent nucleus? Parent nucleus mass number means they are going to ask about that mass number for that S mass number for the X A. So they are asking about that what is the value of A. Okay. So parent nucleus means that X, as I already told you that parent nucleus is X and daughter nucleus will be Y. So that means if it is asking that what is the mass number for parent nucleus, that means they are asking about the value of A. Okay, so this is the question here. So what will be the answer for that question? Okay, the question's answer will be basically given here in that expression. I am writing this expression in a little more detail. Q equals to T into 1 plus M alpha by MD. Okay, it was already discussed in the previous class, but still I am writing a little bit here, M alpha divided by MD. So what is basically M alpha and what is basically MD? M alpha is the mass of the alpha particle and MD is the mass of the daughter particle. So if I just calculate a little bit here, and what is T and what is Q? T is the kinetic energy for alpha particle, and Q is basically the Q value of the reaction. So if I just write here something means like if I write here a little bit mathematics, that MD, then MD plus M alpha. Okay, so the MD plus M alpha is nothing but the MA. That means not A, basically I can write MP. So MP means the parent nucleus mass, and it will be MD. So MD is what? MD is nothing but M P divided by MP minus 4, because MD plus M alpha equals to MP. So MP will be MD minus, sorry, MD will be MP minus M alpha, and M alpha is 4. So that means we can write MD as MP minus 4. So why I am writing this type of things? Because if I am just writing here the final expression, that Q equals to T into MP divided by MP minus 4. Why I am writing like that? Because in our expression T is given, Q is given, nothing more is given, and we already know that for alpha particle the mass will be 4. So that means these three data are given here, but there is nothing mentioned about MD. So we don't know what is the mass of that MD. So what should I do? We are just giving all these expression in terms of MP, so that we can find the value of MP, because obviously MP is given, I mean like MP is asking by them to us. So this is the main question, main expression for that question. So Q equals to T into MP by MP minus 4. Now as I already know that Q is given here in that expression, T is also given, and 4 is obviously known, 4 is a number. So we can find what is the value of MP here. Okay. So in that sense I can say that this type of expression is the main expression for calculating the question, and if I just put the values of T, Q, then we can find the value of MP here. So a little bit calculation is there. Yes. So as I already told you that Q equals to T into MP by MP minus 4. So MP is the mass of the parent nucleus, and given that Q equals to 7.82 and T equals to 7.68 MeV. So M alpha will be 4. So the value of MP will be, just calculating, just putting the values here. I am just going to calculate the value of MP, and the value of MP will be basically nothing but 223.42. But this is not exactly the answer. The answer should be in integer form. So the answer will be 223. Just a minute. So the answer is 223, basically nothing but because 223 is an integer, it's the nearest integer of the 223.42. So the mass number for the parent nucleus is 223. So this is about the first question. Now coming to the second question. The second question is in the beta decay of SN127 to SB127, the maximum kinetic energy of the electrons emitted is found to be 3.2 MeV. If the atomic mass of SN127 is 126.910360 U, the atomic mass of SB127 will be what? So this is the question. So this question is a very simple question, but still there is a simple trick. So I am going to say about that trick here, that what is the trick in that question. Okay, so coming to the space here. So the question was, I think you already understand the question. Okay, I am just telling again the question. So the question is that in that beta decay, like beta decay means SN 126 going to SB 127 plus beta minus 1 0. So beta minus 1 0 is nothing but an electron. Okay. So this type of things is there in beta minus decay. So in that beta minus decay, it is saying that the maximum kinetic energy of the electrons emitted is found to be 3.2 MeV, and if the atomic mass of this one, like SN127 is given, atomic mass is given. So we are going to focus about this term, the atomic mass is there. Okay, then what will be the atomic mass of Sp127? So this is the question. So what should be the answer for that question? Okay. So what was that? Sn, I am writing again that Sn to Sb plus, let's say electron. Like electron is my beta minus 1 0. So electron minus 1 0. So what is the value of Q? Like Q value expression is what? Q value expression is nothing but the mass means what? Mn means nucleus mass of Sn minus Mn Sb minus M of E, right? This is the expression for Q value. But why I am writing here Mn explicitly? Mn means the mass of the nucleus of Sn. It is not that the atomic mass of Sn. The atomic mass and the nucleus mass is different. So in this question, basically the trick is we have to know the difference between atomic mass and nucleus mass. So what is atomic mass basically? Like here, see, let's say X, Z, A, any particle. So here what is that expression saying us? That if I am going to tell about the nucleus mass of X, then we can write that Mnx. But what will be the value of atomic mass here? Let's say I am writing atomic mass as Max. Like it's a very simple notation. There is nothing with that Ma and Mn. So Ma is for atomic mass for X. So what is the expression for Max? The Max expression will be like Z into Mn plus A minus Z into M. Sorry, it should be MP. Just a minute, it's a typo. So Z into MP plus A minus Z into Mn plus what? Plus Z into Me. Because the atom is like, atom consists of three things. One is proton, neutron and electron. So what is basically the atomic mass? Atomic mass is the sum of that each and every particle content. So that means this is for the proton mass, this will give us electron mass, and this will give us neutron mass. Okay, so that means as a whole it is a atomic mass. So what is the difference between nucleus mass and atomic mass? See, this portion Zmp plus A minus Z into Mn, this whole portion is nothing but Mnx. Why Mnx? Because in nucleus, obviously proton and neutron is there is no electron inside that nucleus. So Mnx is about this first two part. And what is the left here? The left one is Z into Me. So that means the expression for between that Ma and Mn is, if I write that atomic mass equals to nucleus mass plus like Me into Z. Obviously Z is the number of protons present in that, number of electrons present in that atom. So this is the expression for atomic mass, and this is the expression for nucleus mass. So if I just write here in that expression that Q, in that expression of Q, that Mn equals to Mn of Sn minus Mn of Sb minus M of E. So what should I write here? I should write here like that, that Q equals to, basically in our question Mn is not given, Ma is given. Ma means atomic mass is given, but nucleus mass is not given. So we have to convert our Q expression in terms of atomic mass. So if I write in terms of atomic mass, then what will be the value? The value will be like Ma Sn, then what, minus Z into, let's say Z into Me, minus Ma of Sb, minus minus plus Z plus 1 into Me minus Me. So this is the expression of Q in terms of atomic masses. So if I just calculate a little bit, then what will be Ma Sn, okay, so Ma of Sn minus Ma of Sb, and you can see that Zme is there and Zme is there, so it will cancel out, and plus Me minus Me it will cancel out. So that means only this term will be there, that Ma Sn minus Ma Sb. So this is the expression for Q value in terms of atomic masses. So this is the main trick of this question, that we have to convert our nucleus masses into the atomic masses. So obviously this is done. So the maximum kinetic energy of the electrons emitted is 3.2 MeV. So there is nothing. Okay. So the main thing is that Q equals to, it should be like, if I write here Ma and Ma. So Q equals to Ma Sn minus Ma Sb, and obviously it is given here. Basically it should not be that line, it will be like that, Ma Sb equals to 3 point, like, sorry, Ma Sn minus Q. So Q will be 3.2 divided by 931.5, because Q, it is in that MeV range, like 3.2 MeV is there. So we have to convert this MeV into that unit. So after converting all these things, then we can have that type of expression, that 126.910360 minus 3.2 divided by 931.5. So this is the answer for the atomic mass of Sb. So as I already see that the expression is matches with the correct answer of A. Where is the correct answer of A? Yeah, the correct answer is 126.906925 U. So the correct answer will be the first one. So the atomic mass of Sb will be that one, 126.906925 U. So this is about the second question. I think it's already understandable by all of you, but still there is some question you have to ask. You can ask me anytime. So this is basically the mass number, like atomic mass of that Sb. Okay. Now coming to the third question. The third question is very similar to the second one, but still I am trying to reformulate that question. The third question is atomic masses of radium. See, here also it is mentioned that atomic masses of radium, radon and astaton are 204.99172 U and 204.98607 U respectively, and the Q factor of the beta plus process is, like, Q value will be what in that beta plus process. So first of all, what is beta plus process, I have to know that, and what will be the expression for Q value of that beta plus process, we have to know that. And after that, just putting the values of atomic masses of Rn and At, we can find the Q value. That's it. So what will be the value, like what is beta plus process? At first I have to see. So what is beta plus process? Oh, sorry. Okay, what is beta plus process here? So what is beta plus? Beta plus is nothing but, let's say x is there, x z a is there. So if I am going to write here beta plus means it is plus 1 0, and what will be that y value? Y will be z minus 1 into a. Okay, so this type of expression will be there for beta plus decay. So there is a difference between beta plus and beta minus decay. The beta plus and beta minus decay has the difference like in that y z minus 1 or z plus 1 value. If beta minus decay was there, then z plus 1 will be in that atomic number, and for beta plus, z minus 1 will be there. So this is the main difference between beta plus and beta minus process. So now coming to the q factor of that equation, and it should be obviously in atomic mass, like atomic mass. It should not be in nucleus mass. Okay, so it should be in atomic mass. So that means if I am writing here, then it will be Ma, and the expression for q beta plus for for beta plus decay in terms of atomic masses, it is like nothing but that MaRn minus MaAt minus 2 into Me. Why it is 2 into Me? In the previous one we were talking about beta minus. In that beta minus, minus 1 0 was there in that outgoing particle, but right now the particle is like here, beta plus is there. So beta plus means it is plus 1 0, and the y value is not z plus 1, it is z minus 1 into a, not into a, z minus 1 in. So that's why if I just calculate the similar thing what I did previously, the expression will be MaRn minus MaAt minus 2 into Me. So this is the expression for q of beta plus. So just write here what is the value of MaRn. It is given in that question, and MaAt is also given, and Me, we all know that Me has a value 0.511 MeV. So 0.511 MeV, but we are going to convert this 0.511 MeV to unit, that means atomic mass unit. So after putting all the values, we can have that type of expression, that is 0.004553 in unit of U. But if I just want to convert this U in the MeV range, then we have to multiply here 0.00453 into 931.5, which is nothing but the 4.24 MeV, and it should be in MeV range because the question was asked in that MeV range. You have to give the answer in MeV. Yes, this one. So that means 4.24 MeV will be there, and is given in that MeV range. So that means the answer will be B. Okay, so this is the third question. Okay, now coming to the fourth one. The fourth question is a little bit tricky, and before going to the main answer of that question, I would like to say about the theory of that question. But still, at first I have to say that what is basically the question is. The question is to consider the beta decay. The beta decay is like K 46 going to calcium 46 plus beta minus. So this type of expression is there for beta minus decay. It is given in that question. So the question is that is this an allowed or forbidden decay, and if it is allowed or if it is forbidden, then what type of allowed decay it is or what type of forbidden decay it is. So is it Fermi type or is it Gamow-Taylor type? So there are four questions, four options. Four options means allowed Fermi, allowed Gamow-Taylor, forbidden Fermi, and forbidden Gamow-Taylor. So before going to the main answer of that question, I would like to say what is basically Gamow-Taylor and what is basically the Fermi type in Fermi type. Okay, so like in that beta transition, beta transition, there is two types of interaction is there. So first one is Fermi and second one is gamoteller, as you already see in that question is also there. So Fermi and gamoteller. So what is Fermi and what is gamoteller type? First of all, we have to see that our transition, our reaction, what is given here, is it allowed or not? This is the first question. So is it allowed or not? If it is allowed, then what type of interaction it is? Is it Fermi or is it gamoteller? If it is forbidden, then what type of forbidden decay it is? Is it Fermi type or is it gamoteller type? So just a minute, sorry. Is it Fermi or is it gamoteller? So what is basically this type of two things is? So let's say a beta transition. In one beta transition, let's say what is there, Z A going to Y, Z plus 1 A plus beta minus. Beta minus is nothing but, I already told, E minus 1 0. So this expression is there for beta minus. So if it is allowed or if it is not allowed, so there are some conditions that this expression should be allowed or this expression should not be allowed. There are some conditions. The first condition is what? We always know that, like we always know that I equals to L plus S. What is L and what is S? L is the orbital angular momentum and S is the spin angular momentum and I is the total angular momentum. So the change in that total angular momentum, that means delta I. If I write here delta I is nothing but II minus IF. What is II and what is IF? II is the initial total angular momentum and IF is the final state total angular momentum. So the change between total angular momentum, that means delta I. Delta I is nothing but, I am writing here, delta equals to delta L plus delta S, because as I equals to L plus S, then obviously delta equals to delta L plus delta S. So any beta transition will be allowed if and only if one condition is there, delta L should be 0. So this is the first condition for allowing any transition. Like if a beta transition will be allowed, then obviously delta L should be 0 for that reaction, for that interaction. So if delta L is 0, so that means in that expression obviously delta I should be delta S, because delta L is 0 here. So that means delta I is delta S. Now coming to the second condition. The second condition is like, so the second condition is like, two possibility will be there. I already told that delta S should be 0, delta S should be equals to delta I and delta L should be 0 for the allow a transition. So if the transition is allowed, then delta L equals to delta S, and two condition may be there, that means delta S may be 0. So if delta S is 0, so that means obviously delta I equals to 0. This one condition is there, and the second condition can be like that, delta S can be 1. So if delta S equals to 1, then delta I will be obviously 1. So why I am telling like that type of expressions and that type of conditions here? Because if delta S equals to 0 and delta I equals to 0, then it should be Fermi type, pure Fermi. And the second condition, if it is followed, then it should be gamoteller. But only, why only these two conditions are valid? Why not the three condition? Why not the four conditions is valid here? Because in that beta transition, what is happening, the in that outgoing particle, what was the outgoing particle? The outgoing particle is z minus 1 a, sorry, z plus 1, like if I am talking about beta minus, then z plus 1 a plus beta minus 1 0 plus there is one neutrino, basically it is an antineutrino. So these two particles are of spin half particle. So this, if these two particles are spin half particle, so we are talking about delta I. Delta I is nothing but the initial and final states spin difference. So we are not talking about these two particles here. So here, like delta I is nothing but the these two contribution. Okay. So in that allowed transition, if delta, obviously there should be two conditions. One will be delta s equals to 0 and other should be delta s equals to 1. Why? Because these two have the spin half particle. So spin half particle means if this type of condition is there, so that means delta s will be 0, 1. And if this type of condition will be there, then delta s will be 0. So and obviously there should not be other value of delta s other than 0 and 1. So that means two condition will be there, one is Fermi type and one is Gamow-Taylor type. So this type of expression should be there, and if this condition is satisfied, then we can say that okay, it is a Fermi type allowed transition. So but if the second one is valid, then we can say that okay, it is a Gamow-Taylor allowed transition. So that type of things is there. Okay, so this is about the allowed transition. But obviously if it is not allowed, if it is a forbidden transition, then what will be the case? Okay, so for the forbidden case, just like right here, forbidden. So for the forbidden case, what is the first condition? Obviously the first condition will be it should not be delta L equals to 0, because delta L equals to 0 is for allowed transition, and for forbidden means there should be there is many forbidden states, but right now I am only going to tell about first forbidden region. So first forbidden region means it should not be delta equals to 0, and it should be like delta equals to, let's say, plus minus 1, plus minus 2, something like that. And the second condition is what? The second condition will be, obviously second condition means there should be like delta, not delta I, delta S. Delta S will be first condition, delta S will be 0 and delta S will be 1. Because these two outgoing particles are electron and neutrino, which are both are spin half particle. So if delta S equals to 0, then obviously it is Fermi, and if delta S equals to 1, then it will be GT. GT means Gamow-Taylor. Okay, so these two conditions should be there. So now coming to a chart here. Yeah, I am making a chart here. Basically the chart is nothing but what I am saying till now, it is just summary of that talk. So what is basically here, see, the transition is allowed. First of all, it is allowed. Allowed means what? Fermi rules delta I. Delta I is 0. If delta I is 0, like, okay, I am saying something more here. Like here Fermi rules. So delta I and parity. Parity is no. Parity is no means what? We all know that parity is minus 1 to the power L. So if delta L equals to 0, so that means parity has no change. Parity is no means it is not that parity is 0 here for all the particles. Parity is no, that means there is no change in parity. So the delta L equals to 0 here. So if Fermi rules says that delta I should be 0, so delta I means delta S should be 0, because for that allowed region delta L is always 0. For Gamow-Taylor rule, obviously what will be the condition? The condition will be delta S equals to 1. So 0 may be there, like, yeah, obviously I will tell what is 0 here saying. So Gamow-Taylor has two conditions, that 0 as well as plus minus 1. So if 0 will be there, let's say in one condition, in one transition there is 0 is the value of delta L, and it is a allowed transition. So that means delta S will be 0. So delta S will be 0, that means it obviously allows the Fermi rules as well as it contains the GT rule. But in that GT rule, one exception is there, that 0 to 0 is not possible for GT rule. So if 0 to 0 is possible in any transition, then it should be Fermi rule, and like it should abide Fermi rule. So for the GT rule, the condition is 0 or plus minus 1, but it should not be that 0 to 0 transition. Like except 0 to 0 transition, all the states with 0 of delta S, it is gamotalar, as well as if it is plus minus 1, then obviously it should be gamotalar, because in a Fermi rule there is no plus minus 1 condition. And the GT rule's parity is no. I already told you what is no here. No means like the parity is not changing here. Now coming to the first forbidden. So first forbidden means what? Obviously that first forbidden region, first forbidden means that delta L should not be 0. So if delta L should not be 0, so that means parity will be changed here. So parity changed means here I can see that here it is written that parity is yes, and for gamotalar also parity is yes. So parity is yes means parity can be changed. Obviously it should be changed because delta L not equals to 0. So this type of condition is there. Now coming to our expression, what is given here. In that question, what is given here, that K, I am just focusing on IP 2 minus, and it is going to calcium 0 plus, and obviously beta minus and neutrino is there, so we are not talking about these things. Like they are just asking that is it allowed or not, is it forbidden or is it allowed. So okay, so at first what should I see here. Oh shit, just a minute. The expression was 2 plus 2 0 plus, sorry, 2 what was that, 2 minus 2 0 plus, okay. 2 minus 2 0 plus. So what is the parity here? Parity changes here. So because the initial parity was minus and the final parity is plus, so that means parity changes here. So that means what? That means that L delta L not equals to 0. What is that? What does it mean? It obviously means that this expression is not allowed. It is a forbidden, first forbidden. Okay, so it is a forbidden interaction. So now coming to the delta I or delta S part. Okay, so here delta L equals to 1. Why it is 1? Because there is plus and there is minus, so that means delta L equals to 1. So what will be the value of delta I? Delta I, we already know that delta S plus delta L. So let's say its value is 1. Obviously its value is 1, it is given here. So what, and delta I is what? Delta I means 2 is there and 0 is there. So delta I is what? Delta I is 2. Okay, so that means there should be something which can give us delta I equals to 2. So I already told you that it is a vector sum. So it is a vector sum, that means it has a value like S mod of delta S minus delta L to mod of delta S plus delta L. So let's say it is a value of 1. So that means it's a 2 value, it can give a 2 value, or it can, if it is a 3, then also it can give a 2 value. But I already told you that delta S cannot have a 3 value. It should be in between 0 and 1. So 0 is not possible. If 0 is there, so that means 0 plus 1 cannot give you 2. Okay, 0 plus 1. 0 plus 1 cannot give you 2. So obviously if we are going to vector sum also, it cannot give us 2. So that means only the one possibility is that delta S should be plus 1. So delta S should be plus 1 is which type of things? It is obviously a GT type, as I already mentioned here. So that means what was that? By knowing the parity, like is it changes or not, we can see that okay, our transition is forbidden. And the second question is that which type of forbidden it is Fermi or Gamow-Taylor. By knowing the value of delta S, we can see that okay, it is a GT, that means Gamow-Taylor forbidden transition. So in that question the option was forbidden Gamow-Taylor. This D question will be the correct one. I think I have said a lot on this question. So if there is any question, you please ask me, or I think I should go to the next question. Like now, if you know that what is Gamow-Taylor and what is Fermi type interaction in beta decay, then we can move to the second as well as third question after that. So I think it is understandable by all of you that what is Fermi and what is Gamow type transition, beta transition. Okay. Now coming to the second, fifth question. Hello. Oh, okay. Thank you. Is there any other message? I did not see the message. Okay, I think I have to see the message. Okay. Only 2 messages was there. Now coming to the fifth question. Now, okay, the fifth question is the atomic masses of xenon, cesium and barium are this respectively. The question is the values are given in brackets. The values are given, values means what? Here the values of IP. IP means 0 plus, 5 plus and 0 plus. We already know that what is 0 plus, what is 5 plus and what is 0 plus again. That IP value is there. So the values of IP are given in the brackets, and which of the following statements are correct? This is the question. Okay, so the question is like the single decay of xenon is not energetically favored. The single decay of xenon is energetically favored, but it is highly forbidden involving large orbital angular momentum of the electron neutrino system. Double beta decay of xenon is an allowed reaction which is energetically favored, and double beta decay of energetically favored, but it is forbidden considering orbital angular momentum. These 4 options is there. So before going to that each and every option, I would like to say something more about that question. So in that question, what is given here, I am writing the same thing here. Okay. Xenon, cesium, barium. Okay. Xenon, cesium, barium. Xenon, cesium, barium. And xenon has, what is that? I think 0 plus is there. And for cesium 5 plus, 0 plus. Okay. 5 plus, and for barium it is 0 plus. Okay, this type of things are there. IP values, I am talking about IP values here. And also some more things are given. The things are 1, 3, 5. Okay, I think I have to, yeah, now I can write here. Just a minute, I am writing these things, and after that I will zoom out again. it is for xenon 135.90722, for cesium 135.90731, and for barium 135.90458, and these all are in U unit, like atomic mass unit. Now I am going to zoom in. Okay, so these three are there. Now what was the question? The question is like, if I am going to tell that xenon conduct a beta minus decay, is it energetically forbidden or allowed? This is the first question, like first option is there. So xenon, if beta minus will be there, then what it will be? It will be cesium. Okay, so xenon will go to cesium. So just I am just writing here, like as you can all see that the first term of all the masses is 135. So I am not bothering about that 135 big number here. I am just talking about that after decimal the data. So here that after decimal data is 90722. It's basically not correct to write like that, but I am just writing like that in a shorthand notation. And for cesium it is 90731. Okay, so you can see that if I write the Q value for this part for this reaction, like obviously in that beta decay what should be there, because beta minus will be there, and obviously a neutrino will be there, and all these things will be there. So if I just calculate the Q value roughly, then what will be the value of Q? This minus this minus this minus this. So the mass of neutrino is nearly zero. Like in nowadays it is saying that it should not be zero, but obviously it's a very small number, and but it is a non-zero value, and it is obviously a positive value. So and also just if Q equals to this one minus this one, if I write it, trying to write, then what is there? My 0.90722 and 0.90731, which will obviously give a negative value, because 90731 is greater than 90722. So we can see that the Q value for this system is negative, and Q value for a system is negative. That means it should not be allowed, it should not be energetically favored. So that means whatever I am talking about, that xenon to cesium with beta minus decay, it should not be possible. It is energetically disfavored. Okay, I think something is there. So the first question was that the single decay of xenon is not energetically favored. Obviously it is not energetically favored. So this option is correct. Now coming to the second option. The second option is that the single decay of xenon is energetically favored, but is highly forbidable, involving large orbital angular momentum of the electron neutrino system. Obviously this second question is incorrect, because it is not energetically favored, as we already shown that Q is negative for that expression. So the B option is not correct. Now coming to the second one, third one. What is third one? Third one is double beta decay of xenon is an allowed reaction which is energetically favored. Is it correct or not? We have to see. So double beta decay. Double beta decay means what? Like here for xenon 54 is there, and for barium 56 is there. So double beta decay is only possible if I go from xenon to barium, right? Barium, sorry. Okay, I think there is no space. Okay, so what is the next one? Next one is the xenon to barium. Now coming to the xenon to barium mass numbers. Okay. So here the mass number for xenon is like 0.90722, and for barium, what was that? 90458. So what will be the value of Q here? The Q value will be obviously a positive number because 722 is there and 0.458 is there. So that means it's a positive value. So if it is a positive value, then it may be energetically favored. But like it may be favored or not, that I don't know. But it is energetically favored. Like if I calculate about that energetically and kinematically, then it is favored. So the third option is obviously correct. The third option means was that double beta decay of xenon is an allowed reaction which is energetically favored. Now coming to the double beta decay of xenon is energetically favored, but it is forbidden considering orbital angular momentum. So now it is energetically favored, we have already proved, but right now we are going to see that it is forbidden or not considering the total orbital angular momentum. So for doing that, so what was that? Like xenon, yes. So xenon was that what? Xenon has the IP 0 plus and barium has the IP 0 plus. Okay. So 0 plus 0 plus, that means delta L equals to 0 because 0 0 plus plus is there. So plus plus is there, that means there is no parity change. So that means delta L equals to 0, and delta L equals to 0 means obviously it's allowed transition, as I already told you before that it should be, it can be Fermi or it can be Gamow-Taylor, but if delta L equals to 0 then it is a allowed transition. So it is a allowed transition. And what will be the type of that transition? The type of the transition is like delta S is what here? Delta S is here 0. So that means it may be Fermi, like it is a mixture of Fermi as well as Gamow-Taylor. So basically, okay, this is the thing that it may be Gamow-Taylor or it may be Fermi, but it is allowed. That is the main question here. So the fourth option is also correct. The no, but is forbidden. Okay, but it's forbidden. It is saying that but it is forbidden considering orbital angular momentum. So that means the fourth option is incorrect. So that means what? The first and the third option is correct, but B and D is incorrect in that question. So I think it's understandable by all of you, but if there is any question, then you can just ask me what is the question of yours. Like here we were just talking about, we were just focusing on that xenon, cesium and barium IP values as well as the mass values. So mass values basically gives us that is it kinematically favored or not, and the IP values are saying that is it orbital angular momentum concept, is it correct or not. So I think the question number 5 is understandable. Now we'll move to the last question for today's lecture. The last question is a very similar type of the previous one, but still we have to do that. The last question is what? That consider the 4 isotopes B, C, like boron, carbon, nitrogen and oxygen with masses this and this respectively. Their nuclear spins and parities are 3/2 minus, 1/2 minus, 1/2 minus and 3/2 minus respectively. Which of the following sentences are correct? So it's basically the similar question I have taught in the previous question, but okay, so for that the similar thing I will do. The similar thing means at first I have to zoom in a little bit so that I can write all the data here in the next page. Okay, what is that? Boron, carbon, nitrogen, oxygen. Boron, okay, boron, I think you all know that C is 6, 7, 8 and it is 5, and the masses, okay, 13, okay, I am writing here 13, 1, 7, 7, 8, 13.00335, 13.00574, 13.02482. It is all are in U unit. Okay, and what is the 3 by 2 half 3 by 2. Okay, 3 by 2 minus 1 by 2 minus 1 by 2 minus, sorry, it is a minus, and 3 by 2 minus. So this type of things are there. Now they were just talking about what? Okay, there is the similar thing that it has 4 options, and we have to choose that which option is correct or not. So the first option is carbon 13 is stable against both beta minus and beta plus decays. Okay, so coming to the C, carbon 6. So carbon 6 is, let's say carbon 6 is beta minus going beta minus decay. So what is beta minus decay? Beta minus decay means it is going to nitrogen 7. So what will be that? 13.00335 and 13.00574. But obviously if I going to calculate Q value here, obviously it is a minus value because this 335 is less than 574. So it is a negative value. So that means the beta minus is not possible for carbon. So what was asking about the first option? The first option said that carbon 13 is again stable against both beta plus and beta minus decays, but we have seen that beta minus is not possible here. So we are not going into the beta plus decays right now, because obviously as beta minus is not allowed, then obviously this A question is not correct. So that means the first option will be incorrect. But obviously you can see that is it beta plus allowed or not with the calculation of that Q values. Like Q values means it should be beta plus, means it should be like here to here. No, sorry, 335 to 1178. So 335 to 1178 means okay, it is possible kinematically that beta plus is stable for carbon 13. Now coming to the second question. Second question is beta minus of nitrogen 13 is not favored energetically. However, its beta plus decay is energetically allowed. So beta minus, it is saying that beta minus is not favored energetically. So beta minus means what? Beta minus means nitrogen can go to oxygen in beta minus decay. So for nitrogen, what is there? The mass is 0.00574. I am not basically writing exactly 13.00574, and it is 0.02482. Okay, obviously it is not possible kinematically because this one is greater than the previous one. So that means for Q value it will be minus less than 0. So that means it is a negative value, and if Q value will be negative, then that beta minus decay of nitrogen 13 is not favored energetically. Okay. Now coming to the beta plus decay. So what is beta plus decay? Beta plus decay means nitrogen can go to carbon. So nitrogen has 13.00574 and 00335. So what was that? Okay, 00574 and 00335. So this may be possible kinematically because it has the Q greater than 0 value, like maybe or U, whatever you can see. So that means that beta plus is allowed kinematically, but beta minus is not allowed kinematically. So the second option, what is written here, that beta minus decay is not favored, however its beta plus decay is energetically allowed, that means it's correct. Okay, now coming to the third one. What is the third one? That boron 13 is most probably a gamoteller type decay. Beta minus of boron 13. So boron 13, okay. So boron 13 is what? Yes, boron 13. So boron 13 beta minus means boron can go to carbon. So here 13.01778 and 13.00335. Obviously it is allowed kinematically. Okay, so this is the first case, it is allowed kinematically. And the question is that is it gamoteller or is it Fermi type? So what is the spin parity here? 3 by 2 minus is there and half minus is there. So minus minus, that means delta L will be 0. So that delta L is 0, that means it's allowed transition for beta transition. And what is the delta S value? Delta S is 1. Okay, so that means it obviously a GT type, that means gamoteller type. So that means the third option, beta minus decay of boron 13, is most probably a gamoteller type decay. It is correct. Now coming to the fourth one, what is beta plus decay of oxygen 13 is energetically allowed, but it is a forbidden decay considering the angular momentum conservation. So beta plus oxygen what? Yes, this one. Beta plus means N. I mean it will go to N. So beta oxygen means 13.02. Okay, 0.02482 and like minus 13.00574. Okay, this is a positive value, so that means it is allowed, that means kinetically allowed. So up to this phrase it is correct, but it is a forbidden decay considering the angular momentum conservation. Is it or not? We have to see. So oxygen to nitrogen. Okay, so oxygen to nitrogen means 3/2 minus to half minus. Okay, where should I write here? Okay, so 3/2 minus to half minus. So 3/2 minus to half minus means delta L equals to 0 here, so that means it's a allowed transition. And what is the value of that? Which type it is? The type is obviously a gamoteller type because delta L is equals to 1 here. So the fourth question, what is given here, that beta plus decay of oxygen 13 is energetically allowed. It is correct, but it is a forbidden decay considering the angular momentum conservation. It is wrong. So that means the total D option will be a wrong option, incorrect option. So because obviously it is also allowed considering the angular momentum conservation. So this is up to the sixth question, and in that sixth question I can say that the summary, as a summary, the B and C, these two are correct and A and D are incorrect. So if there is any question about that sixth question, you can ask, or obviously this was the last question for that today's lecture. So if there is any question, you can just ask me. The second last question and the previous one question is a very similar one, so that's why in the last question I did not take that much time. So I think you all can understand. Okay, there is something. Okay, so I think you understand the question clearly and the answers also. If there is any question, then you can just ask, or otherwise the lecture will end today and we will meet in next week.
Ma'am, can I ask the recent video of the course related with recent video of the course like accelerator and reaction, nuclear reaction?
Sorry, I can't hear you. I think my voice is your voice is breaking. Can you hear me?
Yes, ma'am.
Okay. Can you please ask the
Uh,
question?
uh, can I ask the question recently video uploaded on the exam portal like nuclear is nuclear reaction and nuclear scattering. It
Nuclear.
is not related to the uh, it is not related with the assignment question.
No, basically I am not talking about present year's assignment questions. I think sorry for because I can't hear you properly. But okay, I think you are asking about the present year assignment. I can't hear you properly.
No. It is not related with assignment, but it is related with the concept of the present video.
It is.
Some it is related with some topic. Just I want to understand some topics of the nuclear reaction, like knockout reaction, transfer reaction, direct reaction, such type of reaction. I want
Okay,
to understand it.
okay. You want to understand such type of theory basic questions, right?
Yes.
Okay, so what you want to understand, like obviously I think like in that previous year things, like what is going there in that previous year nuclear and particle physics course, sir is already taught these things, like whatever I have told you right now, up to these things sir already told you people. So basically I am just trying to improve your understanding in that topic again by considering some of the important questions of this. Okay, so this is the main motivation of my lecture here. But obviously if you want
Okay.
some more thing from me, obviously I can tell you, no problem on that. So I think today it is over, today's time is over. So if you want to know something more from me, then you can tell me, I can tell you obviously in the next week. Like theory based question, I can't
Okay.
tell, I
Yes,
can't
yes.
tell you, I can't tell you anything about present assignment. Okay, like present assignment
No,
means
no, no,
you
no.
have to
It's it.
do present assignment by yourself. It is not like that I am telling the
Yes,
answer
yes,
and I am telling the how to do the questions. It is not like that. So but obviously if
yes.
theory has some problem, then you can ask me, I can answer of that question. Okay.
Yes, 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 yes. Please, ma'am, just I want some discussion on the direct reaction and the trans compound reaction.
Okay, direct reaction and
Compounded
compound
reaction.
reaction.
Yes, yes, yes.
Okay, 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 okay. Sure, sure. Like today the time is over,
Why?
so we will talk in the next week about that. Okay.
Yes. Actually, ma'am, I am a NET aspirant. So, and this is the this topic is including the syllabus of the NET. So, like, I want to discuss with this.
Yeah, yeah, sure, sure, sure. Okay, obviously. No problem. Direct reaction and compound reaction you are talking about. So we will discuss in the next week that what is basically direct as well as the compound reaction. Okay.
Yes, yes. I will wait, ma'am.
Okay. I think there is not that more questions. Like if today's session has some problem or doubt, you can ask me right now. Then we can discuss on that also.
Actually, ma'am, I have attended the past just the time of first session. So the same person is discussing. So that's no question here.
Okay.
Because again and again we are saying two times the same question there.
Two times the same question means what? Like I was talking
And that
about.
is same, and that means the two session is covered today for nuclear and particle physics.
Yeah, like previous one, some ma'am was there and she was just talk.
Yes.
Yeah, yeah. Actually, obviously, it was a consequence that in the same day it was doing. So okay,
Yes.
what should we do? Uh,
Then yes.
it's a consequence that like it's a coincidence, you can say like that. It's a coincidence that I and she is talking the same thing in the same day. So okay.
Same question and the
Yeah, same
all are
questions
same question.
obviously. Yeah. But I think like some of the students are like that, they are not, they cannot join in the previous lecture, they are joining in that lecture, or it may be
Yes,
possible
yes,
that
yes.
previous ma'am has some new student which is not in my class, so that type of things may be there. So but for your case,
Yes.
you are the same one who already attended the two same
Yes.
classes.
Yes.
So no problem. Like if you cleared this in that in that session, again you are coming here, so that means it's a like double checking of your answers as well as double,
Yes, yes.
yeah, something you can say like that.
Yes.
Okay, so I think there is no question. So
Okay, ma'am.
okay,
Thank you.
we can end the session to for today, and we will meet on next week. Okay, bye bye.
Okay.